Good day, everyone. Today we are embarking on the second part of our journey through the fundamentals of thermal radiation. In our previous session, we established the core microscopic and directional frameworks of radiation. Today we are going to bridge that core physics with macro-scale applications, moving all the way from specific material surface properties up to planetary heat transfer systems. Over the next 12 to 15 minutes, we will break down these complexities into highly actionable engineering principles. Let's start by laying out our core benchmarks. Let's review our roadmap for this segment to understand our key learning milestones. First, we will define physical mechanisms to solidify our understanding of thermal radiation as a fundamental electromagnetic wave phenomenon. Second, we will analyze spectral distribution to map out exactly how wavelength, temperature, and emissive power interact in real systems. Third, we will evaluate real versus blackbody surfaces, contrasting idealized radiators with actual engineering materials and varying surface configurations. Finally, we will learn how to quantify directional flux, giving you the mathematical tools to calculate three-dimensional radiative intensity and determine net environmental heat exchange. By hitting these four targets, you will be fully equipped to model complex thermal interactions, from simple industrial coatings to global environmental systems. To model a radiating system accurately, your very first task is to classify how the radiation interacts with the material's bulk volume. This brings us to our first major physical distinction: surface phenomena versus volumetric phenomena. Look at the diagram on the left side of the slide. For opaque materials, such as standard industrial metals, wood, or structural bricks, thermal radiation interacts exclusively at the immediate surface boundary. Incoming rays are either reflected or absorbed right at the skin, meaning the radiation does not penetrate into the interior. Consequently, for opaque bodies, emission and absorption are treated strictly as two-dimensional surface conditions. Now contrast that with the diagram on the right. For semi-transparent materials like glass, quartz, or water, radiation penetrates deeply. Here, the entire volume of the material actively interacts with the radiative rays, absorbing, scattering, and emitting energy throughout its bulk thickness. As engineers, identifying which mechanism dominates dictates whether we use a simple surface boundary equation or a complex volumetric model. Because real surfaces are imperfect radiators, we use a scaling factor called emissivity to measure their efficiency against a perfect blackbody. This slide organizes how emissivity changes depending on our analytical lens. Direct your attention straight to the central highlighted box. The top text defines emissivity as the ratio of radiation emitted by a real surface to that of an ideal blackbody at the exact same temperature. Immediately below this text, the central equation defines the absolute thermodynamic boundaries of emissivity, stating that its value must always fall strictly between 0 and 1. Now let's look at the four surrounding quadrants to see why real surfaces are so complex. The top left quadrant defines spectral emissivity, which varies based on a specific wavelength. The top right quadrant defines directional emissivity, showing that efficiency changes depending on the viewing angle relative to the surface normal. The bottom left defines total emissivity, which integrates performance across all wavelengths, while the bottom right defines hemispherical emissivity, averaging performance across all spatial directions. The key insight summarized at the bottom reminds us that real materials are non-gray and non-diffuse. Their performance changes with wavelength, temperature, and angle simultaneously. To make real-world engineering problems solvable without supercomputers, we rely on specific simplifying assumptions. Let's look at the matrix on the left to see how these approximations are categorized based on wavelength independence and directional independence. In the top left square, we have a true real surface, where emissivity is a variable function of both angle and wavelength. If we assume a material's emissivity is completely independent of wavelength, we move to the top right square, which defines a gray surface approximation. If we assume it is independent of direction, we move to the bottom left square, which defines a diffuse surface. When we combine both simplifications into the bottom right square, we get a diffuse gray surface model, where emissivity is treated as an absolute constant. Now look at the graphical proof on the right to see what this looks like visually. The solid black curve represents the smooth, idealized spectral emissive power of a blackbody. The highly irregular, jagged gray dashed line traces a real surface, showing massive real-world volatility. The smooth, magenta dashed line represents our gray surface approximation. Notice how the gray surface curve perfectly mirrors the profile of the blackbody curve, but is scaled down uniformly. This graph proves that while a gray surface approximation isn't perfectly real, it provides an elegant, highly manageable average for engineering calculations. Let's take a closer look at how directional angles alter emission efficiency. This graph plots directional emissivity on the vertical axis against the viewing angle on the horizontal axis, ranging from 0 degrees at the normal vector to 90 degrees at the grazing edge. Look at the top curve mapping nonconductors, such as ceramics, plastics, or oxides. The upper call-out text box defines this behavior. For nonconductors, emissivity remains high and relatively constant across almost all viewing angles, experiencing a sharp, precipitous drop only as you look parallel to the edge. Now look at the lower curve tracking electrical conductors, like polished metals. The middle call-out box defines this profile. A conductor's overall emissivity is naturally low, but it spikes sharply at steep, grazing angles between 70 and 85 degrees before collapsing to 0. To bypass these complex angular swings in daily practice, look at the highlighted box running along the bottom. This statement defines standard engineering practice. We commonly assume surfaces are perfectly diffuse emitters and simply utilize their normal direction values, where the angle is equal to 0, as a conservative baseline. When an incoming radiation flux, known as irradiation, strikes a material boundary, it splits based on the laws of conservation. As the central diagram illustrates, an incoming band of irradiation is divided into 3 distinct parts. A portion is reflected away from the surface, a portion is absorbed into the material skin, and a portion is transmitted completely through the body. Let's look at the mathematical rule structured inside the white box at the bottom. The top equation within this box defines the total irradiation balance, showing that the total incident energy must equal the exact sum of the absorbed energy rate, the reflected energy rate, and the transmitted energy rate. Right below it, highlighted in bright pink, is our core conservation law. This primary equation defines the surface property conservation rule, stating that the total absorptivity plus the total reflectivity plus the total transmissivity must equal exactly 1. Finally, look at the parenthetical note at the very bottom. It defines the rule for opaque surfaces. Because transmissivity drops to 0 for solid metals or bricks, the conservation law simplifies beautifully, stating that absorptivity plus reflectivity must equal exactly 1. This means any increase in a surface's reflectivity directly reduces its ability to absorb incoming environmental heat. Building on our conservation properties, we must look at how surface conditions and external sources alter real-world behavior. This slide highlights 2 critical, real-world lessons. Row number 1 illustrates how surface geometry impacts reflection. Diagram A shows an actual or irregular surface, where an incoming beam is scattered wildly into chaotic directional paths. Diagram B shows an ideal diffuse reflector, which distributes reflections uniformly across a perfect hemisphere. Diagram C shows a specular reflection, typical of highly polished mirrors, where the angle of reflection perfectly equals the angle of incidence. Now move down to row number 2, which demonstrates how source temperature impacts absorption. Look at the architectural graphic. When low-temperature radiation leaves local trees or buildings and strikes the roof, the surface exhibits a high absorptivity value of 0.9. However, when ultra-high-temperature radiation leaves the sun and strikes that exact same roof, the absorptivity drops significantly to 0.6. The highlighted text box on the right defines this critical lesson. Absorptivity is highly dependent on the temperature of the radiation source itself. You cannot treat a real material as perfectly gray across vastly different environments. To connect a material's absorption performance directly with its emission performance, we look to one of the bedrock laws of heat transfer, Kirchhoff's law. Direct your attention to the large formula framed at the very top of the slide. This equation defines Kirchhoff's law, stating that the total hemispherical emissivity of a surface at a given temperature is exactly equal to its total hemispherical absorptivity for radiation that originates from a blackbody at that exact same temperature. To see why this holds true physically, look at the thermal equilibrium system mapped out below. The bullet points on the left define the mathematical state of an object placed inside an insulated, isothermal enclosure. The first bullet defines the energy absorbed by the body, while the second bullet defines the energy emitted by the body. As the final text callout on the bottom right explains, because the body is in a state of thermal equilibrium, its temperature must remain absolutely constant. Therefore, its rate of energy absorption must perfectly balance its rate of energy emission, providing the ultimate physical proof that its absorptivity equals its emissivity. Now let's transition from localized surface physics to macro-planetary heat transfer, beginning with the primary energy source of our solar system. This diagram maps out the geometric relationship between the Sun and the Earth. Let's follow the numbered callouts on the right. Box number 1 defines the Sun as a massive nuclear reactor operating via continuous hydrogen-helium fusion, reaching an internal temperature of 40 million Kelvin and dropping to an effective surface temperature of 5,780 Kelvin. Box number 2 defines the blackbody match, noting that at this surface temperature, the Sun's radiant output perfectly mirrors a mathematical blackbody curve. Now look at box number 3 at the bottom right. The equation enclosed here defines the total solar irradiance, or the solar constant, establishing its value at exactly 1,373 watts per square meter. This metric represents the raw, unattenuated solar power striking a 1 square meter flat plate positioned at the outer edge of Earth's atmosphere. This is the baseline energy entering our planetary system. While 1,373 watts per square meter hits our outer atmosphere, the energy that actually reaches us at ground level is heavily filtered. This graph plots spectral irradiation on the vertical axis against wavelength on the horizontal axis to illustrate planetary atmospheric filtering. The top dashed curve represents the ideal 5780 Kelvin solar blackbody profile in space. The solid, highly jagged purple curve beneath it maps the actual solar radiation reaching sea level on Earth. Notice the massive absorption valleys carved out by atmospheric gases. On the far left, the arrows point to the ozone region, which absorbs almost entirely within the ultra-short ultraviolet band, acting as our planetary biological shield. In the center, a sharp drop points to oxygen absorption, creating a highly localized narrow band. To the right, multiple deep valleys point to water vapor and carbon dioxide molecules, which thoroughly dominate absorption across the longer infrared wavelengths. The summary block at the bottom defines the net result of this atmospheric interaction. Due to atmospheric scattering and selective gas absorption, solar irradiance is attenuated from 1,373 watts per square meter in outer space down to approximately 950 watts per square meter at the ground on a standard clear day. This selective atmospheric filtering is the exact physical mechanism responsible for the greenhouse effect, an essential concept for both environmental science and solar engineering. Let's look at how it works using these two diagrams. On the left, we see a spectral performance curve plotting transmissivity against wavelength for standard glass. Notice that the curve is flat and exceptionally high, sitting above 0.9 throughout the shortwave visible light band. However, as soon as wavelengths push past 3 micrometers into the long-wave infrared region, the curve crashes to zero. This graph proves that glass is a highly non-gray spectral filter. It is completely transparent to visible light, but totally opaque to infrared radiation. Now look at the physical schematic on the right. High-temperature solar radiation, which consists of short wavelengths, passes right through the transparent glass barrier. Once inside, it strikes the interior surfaces and turns into heat. Because these internal surfaces are at lower temperatures, they emit radiation back outward at much longer wavelengths. But remember our glass curve. The glass is completely opaque to long-wave infrared radiation, trapping the energy inside. The text callout defines this as the mechanical foundation of the greenhouse effect, causing a massive internal thermal energy buildup. To perform an actual engineering energy balance on an outdoor structure, such as a building roof or a solar collector, we must account for two separate downwelling environmental fluxes. Look at the top half of the slide, labeled solar incident radiation. The diagram shows that solar energy arrives via two distinct paths: direct solar radiation coming undisturbed from the sun, and diffuse solar radiation scattered by clouds and the sky. The equation on the top right defines the total incident solar energy on a surface, mathematically combining the directional rays scaled by the cosine of our zenith angle with the multi-directional diffuse rays. Now look at the bottom half of the slide, labeled atmospheric emission. The Earth's atmosphere contains gases that absorb heat and emit their own thermal radiation downward. To make this calculation manageable, we model the sky as a single entity. The equation inside the bottom right box defines atmospheric emission by treating the sky as a fictitious blackbody evaluated at an effective sky temperature. As the text callout notes, this effective sky temperature ranges from a cold 230 Kelvin on clear nights up to 285 Kelvin on warm, cloudy days. Now we arrive at the mathematical peak of our lecture, where we synthesize all our surface properties and environmental fluxes into a single master equation. The large formula centered on this slide defines the net radiative heat exchange for an outdoor surface exposed to the open sky. Let's analyze this master equation by tracing the three sequential bracket callouts from left to right. Bracket number 1 points to the first term on the left side of the equals sign. This section defines solar absorption. It represents the energy sourced directly from the sun, which is heavily dependent on the total incident solar radiation, multiplied by the object's specific shortwave solar absorptivity property. Bracket number 2 points to the middle term of the expression. This section defines atmospheric absorption, representing the incoming long-wave energy absorbed from the sky. Notice the text inside callout box 2. Because of Kirchhoff's law, which proves that emissivity equals absorptivity at equivalent infrared temperatures, we can elegantly substitute our material's emissivity value directly into the equation to represent its long-wave absorptivity. Finally, bracket number 3 points to the final subtracted term on the right. This section defines surface emission, representing the raw thermal energy that the object inherently radiates away into the environment based on the Stefan-Boltzmann law and its own absolute surface temperature. This master equation is what allows you to predict whether a surface will heat up under the noon sun or cool down via night sky radiation. To close our discussion, let's look at the grandest application of these principles: our entire planet. Earth is fundamentally a massive thermodynamic engine, powered by radiation. Look at the global hydrological cycle, mapped out on the left. Solar energy heats the oceans, driving evaporation. This evaporated moisture rises, forms clouds, releases energy, and falls as rain into high reservoirs. That water then flows down through penstocks, spins hydroelectric turbines, generates power lines, and returns to lakes and oceans, while atmospheric temperature differences generate global winds. Let's read the analytical conclusions on the right. First, virtually all renewable energy systems, including hydroelectric, wind, solar power, and ocean thermal gradients, are fundamentally just indirect manifestations of solar radiation. Second, this continuous planetary engine relies entirely on the continuous input of solar radiation interacting with Earth's localized surface properties, namely absorptivity, reflectivity, and transmissivity. The final highlighted box defines our core takeaway. A complete mastery of these fundamental radiative surface properties is an absolute prerequisite for designing any engineering system capable of successfully harnessing this global energy cycle. As we look at the beautiful visual on this slide, showing wind turbine networks and solar panel arrays operating together under the sun's rays, it drives home the practical reality of our field. When you design a solar panel, you are directly manipulating shortwave solar absorptivity. When you model the structural cooling of wind turbine nacelles or optimize the thermal efficiency of local power grids, you are managing net radiative exchange against the effective sky temperature. The abstract equations we have mastered over the last 15 minutes are the exact mathematical tools used by modern engineers to design clean infrastructure and advance global sustainability. Let's summarize our final takeaways. That concludes our comprehensive analysis of thermal radiation fundamentals and planetary energy systems. I want to leave you today with the insightful quote centered on this final slide. Heat is a study of exchange. It reminds us that energy, like knowledge, is most powerful when it flows from where it is abundant to where it is needed. As thermal engineers, your career is dedicated to guiding that flow safely, efficiently, and sustainably to power human innovation. Thank you all for your time, your focus, and your excellent participation throughout this session.